Let's jump right into this explainer. Today, we're diving into an absolute masterpiece of biological engineering, the human eye. It's a mind-bending reality, really, how this tiny organ functions exactly like the ultimate high-tech camera, capturing light and instantly translating it into the dynamic visual world we experience every single second.
So you've got to ask yourself, how exactly does a living biological organ act like a complex camera? I mean, think about it. A regular camera needs perfectly clear lenses, a variable aperture to control lighting, and a sensor to capture the image. Our eye does all of this using living cells. And here's the truly crazy part. It stays optically clear without relying on traditional blood vessels. If it had blood vessels right in the front, well, they'd completely obstruct our vision. So it has to rely on this highly specialized internal support system to survive.
To see how this works, we're going to trace a single photon of light from the outside in, navigating through 5 key steps. 1. The protective outer shield. 2. Chambers and vital fluids. 3. The optical diaphragm. 4. The sensory canvas. And finally, number 5, the visual pathway. Now, the crucial thing to map out in your mind before we get too deep is that the wall of the eye is built on 3 foundation coats, or tunics, kind of like layers of an onion. On the absolute outside, we've got the tough, fibrous tunic. Right under that is the vascular tunic, or the uvea, which brings in the nourishment. And on the very inside is the neurotunic, the sensory retina. Literally, every structure we're about to look at belongs to one of these 3 foundation layers.
All right, moving right into Section 1, the protective outer shield.
Notice how the eyeball, which is essentially a slightly squashed sphere, rests perfectly within this pyramid-shaped bony orbit. And those eyelids? They are literally acting as biological windshield wipers. With every involuntary blink, they sweep newly formed tears across the surface, washing away microscopic debris straight into our lacrimal drainage system. This constant resurfacing is absolutely critical to keeping that outer optical layer pristine.
And that outer window is the clear cornea. It's doing the heavy lifting here, providing about 75 to 80% of the eye's refractive focusing power, while the sclera acts as the tough, white exoskeleton. What is so incredible about the cornea is its absolute transparency, which comes from its intensely uniform spacing of collagen fibrils. And, like we mentioned, no blood vessels. It relies completely on the tear film on the outside and fluids on the inside to stay alive.
Which brings us to Section 2, Chambers and Vital Fluids.
Because that optical pathway has to remain totally crystal clear, the aqueous humor steps up and basically takes over the job of blood. It circulates critical nutrients to the inner tissues and clears away the junk. It fills both the anterior chamber, so the space between the cornea and the iris, and the posterior chamber, just behind the iris. The ciliary body is constantly pumping this fluid out, delivering a vital lifeline of glucose and oxygen to the avascular cornea and lens while flushing away waste like lactic acid.
Okay, Section 3, the optical diaphragm. Just like a photographer adjusting a camera lens, our eye has its own built-in exposure mechanism. Look at the physical layout here. The iris is acting as a variable diaphragm, creating this central aperture we call the pupil. And that pupil rests directly against the front surface of the crystalline lens. Actually, the edge of the pupil functions like a one-way valve. It lets that aqueous humor we just talked about flow forward, but stops it from flowing backward. Now, the whole iris is roughly 12 millimeters across, but the pupil normally rests at a precise 3 to 4 millimeters. That's just to regulate the exact amount of baseline light hitting the back of the eye. But of course, that number dynamically shifts. Using tiny sphincter and dilator muscles, the iris is constantly adjusting to ambient light. Step out into bright sunshine, boom, those muscles instantly constrict the pupil to nail the perfect exposure and depth of field. Suspended right behind that pupil by these tiny, delicate zonular fibers is the crystalline lens. It's made up of a capsule, cortex, and nucleus, and it actively changes shape to fine-tune our focus. Again, wonderfully transparent and completely avascular. When the ciliary muscle contracts, it changes the tension on those zonular fibers, physically altering the curvature of the lens. We call this accommodation, and it's what lets you seamlessly shift your focus from a distant skyline right down to the phone in your hand.
On to Section 4, the sensory canvas.
So our perfectly focused photon of light finally hits the film of our camera. This sensory canvas, the retina, is where the real magic happens. It is taking raw, physical light energy and transforming it into actual electrical nerve impulses. The retina is incredibly thin and delicate, yet it's backed by the highly vascular choroid.
That choroid is delivering the massive amounts of oxygen these photoreceptors demand to pull off these rapid-fire energy conversions.
If you look directly into a living eye, you can see this exact tissue. See that bright spot on the right? That's the optic disc. It's the exact exit door where all the nerve fibers bundle together to leave the eye. And because it's totally packed with nerves and blood vessels, there is literally zero room for photoreceptors. So we all have a natural blind spot right there. Meanwhile, that darker area in the center, the macula, is densely packed with specialized cells to give us our sharpest, high-def central vision.
To put this into perspective, think about trying to match your socks in a dark closet. You can't see the colors, right? That's because of our two distinct photoreceptors, rods and cones. The rods are insanely sensitive to low light, so you don't trip in the dark, but they give us zero color perception. The cones, on the other hand, which are packed into that central macula, need a lot of daylight to activate, but when they do, they give us spectacular, vibrant color and the ability to read tiny text.
Which takes us to our final step, Section 5, the visual pathway. Here's a wild thought. Vision itself actually happens in the back of the brain. The eyeball is really just a sophisticated antenna. The electrical signal has to journey from the optic nerve, get sorted at the optic chiasma, and finally land in the visual cortex. The actual recognition of shapes, interpreting motion, the conscious experience of seeing, all of that happens after the signals arrive deep in the occipital lobe. Take a second to trace this incredible wiring map. Right there in the middle is the optic chiasma, where half the nerve fibers actually cross over to the opposite side of the brain. This specific routing means the left side of your brain processes the right visual field of both eyes and vice versa. It is this exact synchronization that seamlessly fuses two slightly different images into one perfect, three-dimensional reality.
It really leaves you wondering, doesn't it? How does this incredibly precise, delicate sequence of anatomical events work flawlessly every single second of our waking lives? From the protective sweep of an eyelid, to the transparent layers focusing a single photon, to the brain painting that reality into our consciousness. Next time you simply open your eyes, just take a moment to appreciate the true miracle of that biological camera you're using. So what else is hiding in plain sight within our own biology?